Welcome to Normality, which is the two sample means lecture. I am Bo Corkins, and this is statistics. So, we saw two sample proportions, and we noticed a lot of similarities between one sample proportions. We are going to notice that a lot with two sample means. Specifically, that our main condition involves normality. So, everything we looked at with normality is the same for two sample means. The difference now is that we have to apply it to each sample. So normal probability plots, in addition to histograms, right? We start with the histogram. Then we want to look at a normal probability plot. The idea is that the values fall on or near a line, all right, a straight line. That is the line y equals x. We need to watch out for that S shape. That's what indicates non-normality. If between the histogram and the QQ plot, you're just not sure, then you should do the Shapiro-Wilk normality test. All right, it is a full hypothesis test. We're going to see a few more examples, but this is all the exact same stuff that we saw in one sample means. Because everything with two sample means has almost all the same translations that come from one sample means and then the expansion that basically we looked at with two sample proportions. We have our population parameters, mu1 minus mu2. All right, using our sample statistics, x bar 1 minus x bar 2, indicating sample 1, sample 2, population 1, population 2. The formulas continue to look more and more difficult. The main concept, though, estimate plus or minus T star times the standard error. Again, we're going to use StatCrunch to identify all calculations. And the big part is in the optional graphs and tables. We're going to select histogram, QQ plot, and Shapiro-Wilk normality test, all right, in order to determine our main condition of normality. Because we have the same assumption that our distribution is normal as valid by the t distribution, which means we need the nearly normal condition to be satisfied, right? We check that via histogram, QQ plot, or Shapiro-Wilk normality test, right? Three big tests. If there is no information and we hope or have reason to assume our data set is not extremely skewed, we can use the large enough condition. The large enough condition is an absolute last resort, right? And I even have it here. It is a last option, but it does exist. Okay, it is the fundamental concept of the central limit theorem that almost regardless of any distribution, if you can verify it meets a couple of base assumptions, then base conditions, then you can verify the assumption of normality. Let's look at an example. Can you tell how much you are eating from how full you are? Or, all right, do you need visual cues? Researchers studying the role of internal and visual cues in determining how much people could eat conducted an experiment in which some people ate bowls ate soup from bowls that secretly refilled. Researchers then had two ordinary bowls, all right, and two identical bowls, all right. So the secretly refilling bowls, right, they were modified to slowly imperceptibly refill as they were emptied. All right, the ordinary bowls, as soon as they got down to a quarter full, someone would come by with a ladle and refill them. So the idea is, do people, all right, judge their portions by internal cues, or if they do, they would eat the same amount, right? So we have the sample mean, size, and sample standard deviation. What does a 95% confidence interval say about the difference in mean amounts eaten? So let's start with identifying information. All right. Oh, look, it's all identified in my table here. I have ordinary and refilling. Just like what we did with proportions, we want to identify the larger sample statistic, all right, as our population 1. So the refilling bowl has a mean of 14.7 ounces. So I am going to call this one sample 1, and this guy sample 2, which means this is N1, X bar 1, S1, N2, X bar 2, S2, right? Standard deviation, sample standard deviation, sample mean, and sample size. Well, that basically, we identified everything right there. That means we can go to conditions. The conditions essentially start and end with the nearly normal condition. I look at the histograms. Looking at this first histogram, all right, of the ordinary bowls, this looks unimodal and symmetric. And that one looks good, and I can end right there. The refilling bowl, yeah, I'm just not sure, right? It's definitely unimodal, but I don't know if that's symmetric. Is this actually skewed? If I'm not sure, that means I would fail that condition. And then I need to look at the QQ plot. Now be aware for the ordinary, and we're checking this for each sample. The ordinary sample is actually done. But, all right, we need to move on. All right, and just to verify, I'm going to double check the QQ plot for ordinary, right? Bowls. So values fall clearly on the line. So even though I didn't need it, that one is verified. For the refilling bowl data set, the values fall pretty close to the line. Again, it's never going to be perfect, but what I don't see is an S. Since I don't see an S, all right, that one is verified. So even though the histogram, which is actually pretty unimodal symmetric anyway, but if you're just not sure, you view the QQ plot. All right. If you're still not sure, you could look at the Shapiro-Wilk normality test, but notice we actually don't have that. No Shapiro-Wilk p-value, which means we can't check that for either. So if these weren't met, then I'd have to look at the sample sizes and notice 2727. All right, large enough condition definitely isn't verified, which means that if these histograms and QQ plots did not look good, we would stop. If all conditions fail, right? Only at least one condition needs to be met for each sample. But if all conditions fail, all right, then we have to stop. So, all right, our statement now. At least one condition was met for each sample, and that's the big part. Actually, we can specify. Histogram, nearly normal for ordinary, and QQ, nearly normal condition for refilling. Now, be aware, that I did purely just to emphasize which one was met, because I only need one. Technically, the histogram and QQ plot were met for the ordinary bowl, but as soon as you meet one, I don't really check anymore, because as soon as I see the ordinary bowl looks unimodal and symmetric, I don't need to look at anything else. You only need one condition. You can continue to verify for practice as we did. All right, okay, at least one condition was met for each sample. So we may assume So we may assume the sampling distribution of x bar 1 minus x bar 2 is normal, all right? And that's the big assumption. So calculations, again, StatCrunch is going to handle it. Most important, like to draw the picture. Confidence interval means probability in the middle. So to StatCrunch we go. Stat. All right, now we go to T-stats. To sample. All right, with summary. B1. Okay, the standard deviation was then 8.4 and sample size 27. 8. And again, all I'm doing is writing down the information from the two samples that we identified as 1 and 2. All right. Notice right here in calculation options, pool variances. Note the default was recently changed to off. The whole idea there, that's what I at least wanted to mention pooled information in proportions, and obviously it's going to come up here in means as well. You don't need to worry about this. Most importantly, make sure that that is turned off. All right. If that ever turns back on, I will post like 10 announcements. But most importantly is that the technology, they operate when you need to pool, when they need to group, when they don't need to group for the calculations. It's not most of the time, all right, all technologies do this, and it's not really our focus. Okay. All right, we are doing a confidence interval for mu1 minus mu2. We got our values. Three 3.18 and 10.22. All right, so we're doing a confidence interval, all right, as it's clearly specified. What does the 95% confidence interval say? So we are 95% confident that the true average now, right? Amount of soup eaten out of a secretly refilling bowl is between 2.18 ounces, right? Our units, and 10.22 ounces more than the true average. Amount of soup eaten out of an ordinary bowl. Right? So that's the whole thing. one average, basically one average bigger than another average by an amount. That's all I'm saying here. All right. That's all this interpretation is, but that's actually a really strong interpretation, right? So what does this say about the mean amounts eaten? Well, secretly refilling bowls, basically we humans do need visual cues, okay? Because if we're not given visual cues and our plates just keep filling up, well, we're going to eat a lot more because you eat with your eyes, partially at least, right? And it is an important thing, all right, to understand about humanity. So, very, very interesting, all right? Interesting analysis and interesting interpretations. Similarly, we can do this, all right, with hypothesis testing. Notice these hypothesis tests look very, very similar to what we saw with proportions, which means when we initially set those up, okay, we need to set those up in context and then convert to what matches the StatCrunch output. And we're going to see that here. Again, yet another, this has got to be the 500th version of this formula, but it is still observation minus the mean divided by standard deviation equals T, okay? Equals T or equals Z, all right? The details are different, but the concept is the same. Our conditions, everything relies on the nearly normal condition, and then last, worst case scenario, all right, you have the large enough condition. Okay. So, do consumers spend more on a trip to Target than Walmart? Suppose researchers interested in this question collected a systematic sample of 85 Walmart customers and 80 Target customers by asking customers for their purchase amounts as they left the store. The data is summarized below and in StatCrunch titled Consumer Spending. So once again, we have a sample size, mean, and standard deviation. It's all about comparing the means. Whichever one has the bigger mean, that should be sample one. I clearly can see that is Target, which means that makes that N1, X bar 1, S1, N2, X bar 2, S2. When I identify them, I'm going to use notation that makes the most sense. Walmart, how about W, right? So, and Target, I'm going to identify with T when I actually create my hypotheses in context, which is always where we start. Identify info is first, but the info is very easily identified. So our hypotheses, HO, HA. It starts, okay, that one is equal to the other. That is how they always start. Then we need to identify what the alternative is, greater than, less than, or not equal to. So do consumers spend more on a trip to Target than Walmart? So notice, Target is the bigger value. That means, right, the inequality should be, right, the alligator should be eating the average of Target. This is absolutely, all right, how you should write your hypotheses, all right, every time. And that's how you would interpret it. If I could just get the output and I didn't need StatCrunch, I wouldn't bother proceeding past this. But because StatCrunch has a couple of steps, we are going, all right, to adjust. All right, so first of all, Walmart is 2, Target is 1. So wherever I had a W, I'm going to turn that into a 2. Wherever I had a T, that becomes a 1. Then, in order to adjust it, so I have mu2 less than mu1. I need it to say 1 minus 2 because that's what StatCrunch always does. So I need to bring the mu2 to the other side. On the left side, I'm left with 0. Mu2 minus mu2 is 0. Less than mu1 minus mu2. Now, one other thing. StatCrunch is kind of sensitive that the 0 is always on the right side. So I need to flip this around. Mu1 minus mu2. When I bring that inequality over, that becomes a greater than 0. These two things say the same. These are equivalent. All right, but a lot of people get messed up by that because I know it's just a basic algebra thing, but a lot of people like mess that up. So, all right, we want to make sure we could do that. Then, now our hypotheses, they become mu1 minus mu2 greater than 0, mu1 minus mu2 equals 0. Getting this set up, getting that equality face the correct direction is the toughest critical thinking part that you have to do. That's the part that everyone struggles with. Because actually making sure your inequality is face the correct direction, that's the part I want you to emphasize. That's critical thinking. All right. And this is what the StatCrunch output should look like. All right. The conditions, again, for each population. In order to do this, we're going to kind of simultaneously do this in StatCrunch because we need the data, right? We have it. We need the data to actually view the values. All right. So again, I get to go to my data. You need to actually search Bo Corkins, right? Consumer spending. Darn it. All right, we have Target, we have Walmart. T-stats, to sample with data now, right? It says sample 1. We identified Target as sample 1. Sample 2, we identified Walmart as sample 2. Hypothesis test, mu1 minus mu2 greater than 0. And I know that seems like such an easy thing. Oh, well, if the p-value is wrong, I just flip it. Yeah, but if you don't have the answer, then you're too late. Then you misanalyze the data. All right. Then in options and graphs, histogram, QQ plot, Shapiro-Wilk, all three of those last options we want to select. Remember to control click, all right, if you're not using an iPad. All right. So starting with the histogram of Target, that looks pretty good. Histogram of Walmart, that looks fantastic. That's actually it. I don't need to look at it anymore. Those two look great. For practice, we're going to do them all, though. So the histogram, unimodal, symmetric. Fantastic. And again, that's as far as I need to go. We're going to take a look at the QQ plots. The Target QQ plot, values fall on the line, doesn't look like an S, looks wonderful. Walmart QQ plots, again, just absolutely fantastic. It's about as good as it gets, right? Data's very, very close to the line. Don't see anything, all right? It looks like an S pattern. I have two values on the extremes that don't almost fall perfectly on the line. All right, Shapiro-Wilk. This is the tough one, and this is the one I want to practice too. Remember, HO says Data is normal. This is a hypothesis test within, right, inference. Data is not normal. And both of them, right, have the same hypotheses. All right, the first one, we're going to look at Target. Second one is Walmart. So the only thing is to make sure we are grabbing the correct p-values. Okay, so back to our initial values. Down here, Shapiro-Wilk normality test for Target. The p-value is 1782. P-value 1782. 9911. And the p-value for Walmart was 9911. So in both cases, right, both those p-values are high. Fail to reject HO at 5% significance level. Reasonable to conclude. Data is normal. So, right, these are or conditions. I just want to keep emphasizing that. And I guess while we're at it, let's check the absolute last one. Large enough condition. N equals, for this was target 80. Again, the large enough condition is weirdly restrictive with means, which is why we tend not to check it. But just because the t distribution is robust, as long as your sample size is reasonably large, like that one, and you don't have information on the others, you can use that as a stand-in. But the point is, all right, all 8 conditions were met, even though, okay, all 8 things to possibly check were all met, even though we only needed 2. We needed 1 for each sample. So, at least one condition was met for each sample. We can assume the sampling distribution of x bar 1 minus x bar 2 is normal. All right. The t statistic and the p-value, we actually already have that, right? That is the initial output here presented in StatCrunch. So, all right, 3.30 and 0006. Let's draw a picture just to verify. All right, the mean in this case is 0. All right, the difference actually recorded is 10. And it is a greater than alternative hypothesis, which means we are shading to the right. That p-value is very, very small, right? If p is low, the HO must go. Reject HO at a 5% significance level. There is strong evidence to show that. Then again, back to context. All I'm going to interpret is this. I'm literally going to say this little algebraic expression in words. The thing is that actually becomes pretty long. It can become pretty long very, very easily. But that's all I'm doing. I'm just saying that in words. You should never say this in words. Do not interpret this as, oh, the true difference is greater than 0. Ugh. Okay? One value greater than another value, whether that's proportion or mean or whatever, okay? But one value being greater than another value or less than or, different than. That's what we want to talk about. All right. There's strong evidence to show that the true average amount spent consumers spend at Target is greater than the true average amount. Right? The true average amount consumers spend at Target is greater than the true average amount consumers spend at Walmart. Mu T is bigger than mu W. That's literally all we said there. And that is the proper interpretation. And that's what I want you to focus on. Interpretation, all right, is everything. Oh, one last little thing before we wrap up here. So like I said, we talked a lot about pooling, right? Which is combining proportions or standard deviations, all right, to make the calculation simpler. I want to be clear that whether you pool or don't pool, all right, it depends on the assumptions that underlie the situation. Now, the good news is we have conditions that we check. From then on, StatCrunch is going to verify all other conditions. So you don't need to worry about pooling, but I wanted to make note because you'll read this in textbooks and see this mentioned often. Don't worry about this part, all right? If you continue in statistics, happy to discuss this further, but it's something to basically say this is outside the scope of this course. Same thing with standard deviation, and actually brings up one other interesting thing. Degrees of freedom, right? When we started one sample means, we said degrees of freedom was sample size minus 1. Very, very simple concept. Well, now that we have two samples, well, it seems that the sum of the two samples minus 2 would make sense. And that's basically what's happening. However, the official calculation is way more complicated. in fact, if you notice the degrees of freedom, 161.14552. It's actually a decimal. It's because precise degrees of freedom calculation requires a horrific looking formula like this. So we again leave that to the technology. Understand the basic concept that it's about the sum of the two samples minus two, just like it was sample size minus one with one sample means. But as we get more complicated, a higher number of samples, the degrees of freedom become more complicated as well. All right. We will leave it there for the day. Thank you very much and have yourself a great day.